So we're going to be talking about proof by mathematical induction, and then at the end of this video I'll give a couple examples of using this technique. So proof by mathematical induction is a proofwriting technique that we use where the premise is you have some hypothesis, P of n, so this is our inductive hypothesis, and then we have some set. So we'll call it set A, and basically what we're trying to do is prove P of n for any A in our set A. And the way we do this is we first look at our base case, which is the smallest value in A. So what we're going to do here is we're going to prove P of, we'll call it A naught, is true. And once we've verified our base case, we then go into our inductive step. And what we try to do here is using P of n, we want to show that P of n plus 1 is true for any n in A. So what this does is we've already proved that P of A naught is true. So if we let A naught equal n, and then we've proved the inductive step, n plus 1 equals A naught plus 1. So therefore P of A naught plus 1 is true. Then if we let A naught plus 1 equal n, n plus 1 equals A naught plus 2. So P of A naught plus 2 is also true. And this will continue across the set A. So what this does is it creates a domino effect. So if the first one is true, then the next one, and then the next one, and then the next one, and so on. And this really just simplifies the proofwriting process for a lot of specific types of proofs, and we'll go into a couple examples now. So for the first example, we're going to be looking at this formula: 1 times 2 times plus 2 times 3 plus 3 times 4 plus n times n plus 1 is equal to n times n plus 1 times n plus 2 all over 3. And we're going to be trying to prove this for the set of natural numbers, so 1, 2, 3, 4, etc. So the way I like to solve these, or prove these, is I start with the base case. So in this case, it would be n equals 1. And what we're going to do is we're going to prove that it's true when n is equal to 1. So n equals 1, so 1 times 2 is equal to 2. And then we can go to the other side, and we want to show that that's also equal to 2. And we get 2 for both of them. So our base case is true. Next, we're going to do our inductive step. So first, we're going to state our inductive hypothesis. So 1 times 2 plus n times m plus 1 is equal to n times m plus 1 times m plus 2 all over 3. And for these ones with a lot of binomials, I actually like to factor them out. So n squared plus n times m plus 2 all over 3. And if we do it again, we get n cubed plus 3n squared plus 2n over 3. And what we're going to want to do is we're going to want to take P of n plus 1, and we want to prove that essentially both sides are equal to each other. So 1 times 2 plus n times m plus 1 plus m plus 1 times m plus 1 plus 1, which is m plus 2. So we'll just start with this side. And we can see that this part is p of n. So it's p of n plus m plus 1 times m plus 2, and that's equal to p of n plus 1. We can simplify this by factoring it out to n squared plus 3n plus 2. So next, what I'm going to do is I'm going to do the same thing for the right side of that equation. So m plus 1 plus times m plus 2 times m plus 3 all over 3. And what I'm going to do is I'm going to factor this out. So n squared plus 3n plus 2 times n plus 3 n cubed plus 3n squared plus 2n plus 3n squared. I'm going to simplify this. And we get n cubed plus 6n squared plus 11n plus 6 over 3. So we are going to go back to the beginning, and we know what p of n is equal to. So we can take that out of this. So n cubed plus 3n squared plus 2n all over 3. And that leaves us with 3n squared plus 9n plus 6 all over 3, which is equal to p of n plus n squared plus 3n plus 2. And we can see that these two are the same, so we have therefore proved this statement. Okay, so in conclusion, mathematical induction requires 2 steps, the first of which is our base case, and the second of which is our inductive step. And to do the inductive step, we want to focus on the inductive hypothesis and use, in a lot of cases, algebra to prove p of n plus 1 is true if p of n